The industry dogma that bigger models always mean better results has hit a hard wall. New research shows specialized tiny models under 1 billion parameters are now outperforming massive giants on high-resolution image editing tasks. This shift forces engineers to rethink their entire approach to production deployment and budget allocation. Today we connect this headline to the engineering trade-offs behind the hype, revealing why clinging to scale at all costs is becoming a liability for modern software teams. When a new AI model drops, the question that matters most is not the leaderboard score or the parameter count. It is whether your stack can run it reliably within budget constraints and which shortcuts will break in production. For years, developers have been stuck in a mindset where they grab the largest available foundation models for every task, assuming brute force scaling solves everything. This approach leads to expensive inference costs and latency issues that degrade user experience. The reality is that many teams are burning significant resources on sledgehammer architectures when a scalpel would do a better job with less overhead. The stakes here involve both your wallet and the quality of your application's output. Engineers currently over-engineer solutions, running massive models for tasks that require only specialized logic. This results in high latency and hallucinations, where AI generates artifacts like floating objects or distorted faces instead of clean edits. A recent breakthrough from Samsung AI Center challenges this assumption directly with a model called Mobile Picasso. While giants struggle to maintain detail above standard resolutions and suffer from these errors, this new architecture delivers 48% fewer hallucinations while improving image quality by up to 35% over existing methods. The mechanism behind this success is not magic, but smarter mathematical design tailored for specific tasks rather than general capabilities. Mobile Picasso uses a technique called hallucination-aware loss during low-resolution editing stages and adaptive tiling for high-resolution upscaling. This prevents the common artifacts that plague larger models by focusing computational power on maintaining structural integrity where it matters most. The results are staggering, with latency speedups of 55.8 times compared to standard cloud-based approaches when processing images locally. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This shift is not isolated, but part of a broader movement toward data-centric compression and architectural specialization. Research from ByteDance Intelligent Creation Lab introduces Dreamlight, a unified model with only 390 million parameters that handles both generation and editing simultaneously. This stands in stark contrast to the billions of parameters found in models like Flux or SDXL, which require massive compute resources just to function. By using in-context spatial concatenation for a single network architecture instead of separate systems, Dreamlight reduces denoising steps from dozens down to just 4 while maintaining high fidelity. The performance metrics are what truly validate this engineering judgment shift. In user tests involving 46 participants, the specialized models showed consistent improvements across quality and speed benchmarks without requiring cloud dependencies. The team achieved a GeneEvil score of 0.72 and an MGEdit score of 4.11, matching the output quality of much larger competitors while running entirely on local hardware like standard smartphones. This means full high-definition image generation or editing can happen in under 1 second directly on your device without any network latency. Understanding why this happens requires looking at the fundamental bottlenecks in current AI infrastructure. As hardware limits constrain parameter scaling, the primary constraint has shifted from model size to the quadratic computational cost of self-attention mechanisms when processing long sequences or high-resolution data. The solution is not simply building bigger chips, but compressing the volume of data processed through smarter algorithms that reduce redundant calculations. This approach acknowledges that efficiency now comes from what we feed the model and how it processes information rather than just shrinking the weights themselves. The implications for software engineering careers are profound because practitioners must learn to match model complexity strictly to task requirements. Engineers who continue to assume bigger is better risk building systems that are too expensive and slow for real-world deployment scenarios. The new judgment call involves asking whether a specific production task actually requires massive scale or if a specialized small architecture can solve it more efficiently. This decision-making process directly impacts the bottom line by reducing inference costs dramatically while eliminating network latency entirely through on-device processing capabilities. Current industry standards often assume that high-resolution editing demands cloud GPUs and struggles with artifacts, but this data proves otherwise for specific use cases. We are seeing a transition where 48% improvements in image quality come from architectural innovation rather than raw parameter growth. The quadratic cost of self-attention mechanisms means that as context length increases or resolution scales up, the computational burden grows exponentially unless addressed through specialized techniques like adaptive tiling and loss function optimization. This evolution forces us to reconsider how we design AI systems for mobile and edge environments where resources are finite but user expectations remain high. The ability to run 48% fewer hallucinations while delivering 4 kilobyte quality edits on a smartphone represents a fundamental change in what is possible without relying on expensive cloud infrastructure. It enables real-time AI features that were previously impossible due to hardware constraints, opening up new possibilities for application developers who need low latency and high fidelity simultaneously. The future of AI deployment lies not in chasing the largest models, but in finding the right specialized architecture for each specific problem domain. By focusing on data-centric compression and task-specific loss functions, engineers can achieve superior quality with significantly reduced costs compared to brute force scaling strategies. This shift represents a maturation of the field where engineering judgment becomes more valuable than simply having access to the biggest compute clusters available today. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.